pushing it back to 0. Does that make sense now?
Trying to visualize that. Kind of.
Okay. It takes time. It's okay.
Yes, thank you.
Right. So now, right, at point A, we know that the shear force is not equal to 0. At point B, it's not equal to 0. Okay. We know that the moment is equal to 0 because of what? Because once you release one point, it will rotate. Okay. So now we realize that omega as a function of x is also equal to 2000x plus by what? 6000. It's like your math, right? You have the same what? Equation. But now, what if Sylvie were to ask you to solve when v is equal to 0 or x equal to 0 is equal to 0, then she give you another boundary condition. So this is like a math problem now, yes or no? So on the left-hand side, she asks you to solve that equation. On the right-hand side, what does it look like? When m is equal to 0, the moment is equal to 0. When m is equal to 6, moment is equal to 0. Can you see the difference now? Right? So now if we just do 3MA3, Sylvie asks you to solve these two equations. So mathematically, it looks like this. Physically, how does it look like? Physically, it looks like this. That is why, right, when I was young, my sister told me, brother, math is a language. This is when I was like grade 3 or grade 4. You know what's my response to my sister? And my sister is 2 years older than me. She told me, brother, math is like a language. This is when I was in grade 3. She was in grade 5. She knew that it was a language. You know what I called my sister then when I was at grade 3? You crazy bitch. What do you mean math is the language? 1 + 1 = 2. What do you mean it's the language? She's right. Yes or no? By looking at the boundary condition, we can draw structure analysis. Amazing. Okay, so I apologize to her. By the way, she's 10 times smarter than me, okay? I'm not that smart. Right. So now we're going to solve for this, right? So we know that some of you are laughing. Yeah, I know. She's the smart one in the family, okay? So dv by dx is equal to minus omega as a function of x. Same thing, okay? So this will be equal to minus what? Minus 2000x. 2000. Come on, do properly, Eugene. 2000x minus by what? 6000. Okay. Then we have the next one is we're going to integrate, right? So v as a function of x, we're going to integrate minus 2000 x minus 6000. Right? So when we integrate, we have minus 1000 x squared minus by 6000 x plus by c1. This is our equation number 3. Now, can we find c1? The answer is no, because our boundary condition does not work for what? The shear force. Right? Our boundary condition will not work on the shear force. Okay? So now we have to, if you cannot do anything, we have to move on. Okay? We cannot say this is engineering. Okay? It's not, we are not a banker. A banker 0 + 0 can be plus 10,000. We are not. We are engineers. Okay. So by right, I'm going to write this is equal to dm by dx. Okay. So next, we're going to integrate again. We're going to integrate minus 1000 x squared minus 6000 x plus by c1 dx. Okay, I forgot my dx. So this is equal to minus 1000 x cubed over 3 minus by 3000 x squared plus by c1x plus by C2. Equation number 4. Now, with this equation, right, we can solve for C1 and C2. So we're going to substitute when x is equal to 0, moment is equal to 0 into equation number 4. Right? So over here we have 0 equal to 0 minus by 0 plus by 0 plus by C2. So we know that C2 is equal to what? 0. Okay. So the next one, we are going to substitute, or from here, we know that m as a function of x is equal to minus 1000 x cubed over 3 minus by 3000 x squared plus by C1x. This is your equation 4a now. Because C2 is equal to what? 0. Okay. And then finally, when we're going to substitute x is equal to 6, m is equal to 0 into equation 4a, right? So this is still equal to 0. So this is equal to 6 power of 3, 6 power of 3 times by 1000 divided by 3 is equal to minus 72,000. I'll do it again. So 6 power of 3 divided by 3 times by 1000 minus 72 minus by 3000 times by 6 squared is equal to 108, 123 plus by 6 C1. Okay. So therefore 72, 123 plus 108, 123 divided by 6. 72, 123 plus, 72, 123 plus 108, 123 divided by 6 is equal to 30,000. So C1 is equal to 30,000. Okay. So moment, therefore, moment as a function of x will be equal to minus 1000 x cubed over 3 minus by 3000 x squared plus by 30,000 x. Okay, so v as a function of x will be equal to what? Minus 1000 x squared. Okay, minus 6000 x plus by 30,000. So this is your equation for B, and this will be your equation 3a. Okay, so this is how your shear force and bending moment equation look like. So once you have this, what do? Okay, let's plot the shear force and bending moment diagram. Let's see how it looks. Okay, so with this, we are going to go quickly into Excel. Okay, we go quickly into Excel. So we are going to plot the equation. Okay, we're going to plot the equation. So we are going to have, we're going to plot the shear force diagram. Okay, we're going to plot the shear force diagram. So we have x. Okay, so 0 equal to this plus by 0.2. Okay, so we are going to plot until 6 meters. So we're going to plot until have we reached 6 meters? We have reached 6 meters. Good. Then we are going to sketch our v as a function of x. Okay, so this will be minus 1000 times by x power of 2 minus by 6000 times by x again plus by 30,000. Okay, so we are going to grab the whole thing. So this is how your bending, your shear force will distribute like. Okay, so this is how it looks like. Insert. Why it looks weird? I think it has to be data. Okay, it looks weird. Hey? Okay. Okay. So this is how our shear force look like. Okay. Then we're going to plot our bending moment. M, the function of x. Okay. So this will be equal. So we are going to do the same thing. Okay. So this is equal to minus 1000 times by x power of 2 divided by 3. Okay. And then minus 6000 times, minus 3000 times by x again, power of 2 plus by 30, 1, 2, 3 times by x again. Okay.
The first one should be power of 3. X power of 3. Yeah.
Times x.
But the first one, 1000 power of 3.
Power 3, yeah? Not power 2, yeah. You're right. Okay, power 3. Thank you. So I'm going to close bracket down here. And I'm going to put bracket down here in case something stupid happened. Okay. So now, how do we know that this is right? Because when x is equal to 6, the moment has to be equal to what? 0. Please be equal to 0. Hey! Okay, so now we have this. Okay, so what you see over here, right? What you see over here, the blue is the distribution for the shear force. Okay, the M, okay, the orange is going to be the distribution for the what? For the bending moment. Okay, and you will see that the distribution at M is when x is equal to 0, x equal to 6, the moment is equal to what? 0. Then this is correct. If it's not equal to 0, there's something wrong with our function. So that is the purpose why we construct or we use what? That's why I enforce you I enforce you to form the shear force and bending moment equation. Okay, now the next part, anyone, any questions so far? No. Okay, so the next part is this: how to find slope and deflection. Okay, so how to determine slope and deflection. Okay, so we are going to apply, okay, we are going to use the elastic curve method. Okay, we are going to use the elastic curve method. So what do I mean by we are going to use the elastic curve method? As I said, I'm not going to derive the formula. Okay, I'm not going to derive the formula. I only want you to look at this equation. Okay, so it's equal to EI d squared y over dx squared is equal to m as a function of x. Okay. This is what we mean by we will apply the elastic curve method.